Hi, my name is Corbin Coyes. I'm the Vice President of Engineering for Q2 ALS for North America. And today we'll be talking about rod pumping in the curve with the Q2 HVS system. So the current production engineering landscape right now, most of the wells are at 90 degrees. A lot of the companies are drilling horizontal, and we frack the wells, and up until recently, normally we've been only able to produce up to 42 degrees with the typical standing and traveling valves. So this limits us with respect to how far we can go in the hole, and with respect to some of the wells that have low fluid levels, and oil companies want to get the rest of the oil out of the ground, as well as for high producing wells, we want to get more head on our pump just to give us more fillage and better production rates. So we have, I think, 35,000 pumps a year on average, and we're starting to see these really start to grow, and I'd say about 1/10 of these now are using these HVS valves. So like I said before, the problem is the valves. They didn't work past 42 degrees. Another thing when we're going around the bend is the friction that occurs around the curve. Another problem is sand bends. They tend to settle between that 45 and 75 degrees. It's called avalanching. They like to settle there. Another issue around pumping in the curve is gas. With gas, that's when the liquid fallback occurs, and gas slugs break out in the angles as well at those steeper angles. Side loading on equipment is obviously one thing that operators are balancing. So they're going to get increased production, but they want to make sure their failure rates remain a very low rate too as well. So why do you pump in the curve? So like I said, oil production, larger head on your pump. The valves themselves don't increase production. There's only a certain amount of area goes through. They do have more area for solids and for production. However, it's just deepening them in the curve, giving us more fluid level and them able to pump more oil out of the ground because of the nature of going deeper into the hole. So we'll start off originally by looking at the old 1938 patent, and this particular insert has ball vibration and tight tolerances. Then we come into the vortex gauges, which are in the majority of a lot of wells out there over the last 20 years, and that's turning the fluid and stabilizing the ball, minimizing the gas breakout as well. So after this, we extended that cage and we changed the shape to have two spheres in a stem instead of a ball. Now we're getting to 45, 70, and 90 degrees. So the forces on the valve systems, if you look at the old API ball, you have a random varied single point forces. When the ball comes down on a seat, there's a small little 90-degree lap for an API ball, which is a bigger ball, and an alt ball, which is a smaller size ball. And when that ball comes down at different angles, you can see these balls come out of the hole, and they're elliptical. They're very hard, so after millions of cycles, you'll see the shape change and then they leak, right? And also when it comes to just longevity of the seats, when you think of a ball under 2,500 PSI, those are the ranges we're at. So really high pressures. When that ball comes down and hits that seat millions of times, you wind up wearing that lap away on the seat. So with the new design, we've got two spheres. They're almost like conical shapes. So they're spherical in the end. There's a flat part on them. And the reason why that flat part is, one, that's the smallest cross section of our pump, so you get more fluid by it. And two, when we machine it, we have to hold it, and a sacrificial diamond grinding wheel machines that to a 10 micron finish. It takes 45 minutes with a sacrificial diamond grinding wheel. So this is some of the hardest metallurgy on the planet. Because we're at that 2,500 PSI, we don't have the luxury to use a smaller Rockwell metallurgy. So initially, we thought it was a fulcrum that put the barbell onto its seat. Hydrostatic pushes the top sphere and the bottom sphere comes in. But recently, after field trials and an extensive lab report that I'm going to go through with you, we realized it's a hydrodynamic effect, and I'll explain that more in the next few slides. Also, one more thing, we have a more predictable, consistent distributed forces. So there's only about a 10-degree play inside there. So when the valve goes to shut, there's a fulcrum effect when it comes to the seat that's still there. So it rides up the seat and doesn't move, and it's consistent and distributed very evenly. It has, I don't know, I think probably around 50 times the surface area than a normal lap does. So you've got a bigger surface area sealing, and you have a tapered piece there too, where the solids can be flushed away before this seats. So like the typical valve function, it's very similar to the conventional rod pump. On the top, you see the standing valve is open and the traveling valve is closed. That is on the upstroke. And then you fill your barrel up with oil, sometimes water, gas, solids. And then when you go downwards on the reciprocation cycle, your travel valve opens, your standing valve closes, and that amount of liquid in that column comes above your travel valve, and that fluid eventually gets to surface. So here's a really interesting lab experiment that we did. We set up a basin with water. We had a PLC, a programmed logic controller, to measure the pressure at each of the nodes on the screen with varied flow rates. And also we had a solenoid where we could measure the amount of gas going into the tubing as well. You'll see that this is horizontal, right? And the next slide we look at it being at 60 degrees. So we wanted to match what happened in the field. We had an operator pumping at 60 degrees. So we moved the valve up into that zone and we wanted to see the fluid profile, the pressure fluctuations that are occurring, and we also looked at different media. On the far left, you'll see a little nanobubble creator. We wanted to create small gas molecules to mimic what's happening downhole at 8,000 feet. We know the gas molecules are small, so we're able to create these nanobubbles to see how it interacts with the valve during the laboratory process. So the laboratory testing had 5 stages to it. We did it with steady state, we did baseline and different media. We tested with reciprocation, which was key for our operators. They don't want steady state with respect to the results that they're looking for. They wanted to see something reciprocate. So for the PLC, we're able to stop and start it and simulate reciprocation. The visual sinusoidal wave is something we want to look at and capture because we know that a vortex past the valve creates low friction on the pipe wall. Guess what? That's more kinetic energy. It's less friction. Bernoulli's equation, you get more liftage and more consistent flow, less gas breakout in your pump chamber. And the most exciting thing about this, which is a step change in production, it's a self-closing valve, which I'll get to in the next few slides. So here's a visual analysis beforehand. So what we did with the nanobubbles is we had to use high-powered lasers because they're so small and the wavelengths are captured by high-powered green light, really illuminated it, and then we had LED lights behind it as well. You see on the left-hand side, you've got chaotic flow, the gas is up top, that's turbulence, right? That's friction on your wall. After the valve, you'll see how everything's even, right? So what that does, that vortex creates a shear plane for all of the shear planes of, if it's just water, it's fine, but the gas illuminates the shear planes here. So you can see a nice even distribution of fluid flow, which gives you more kinetic energy in your pump and very little gas breakout as well. So this was kind of a neat aha moment. The scientists I was working for, I always like to go to the end and come back because I'm in a hurry to see what the results are. But they said, no, Corbin, let's start from the beginning and let's make sure that all of your baselines are done so we can compare them to your valve. So we did baseline RO. RO stands for reverse osmosis, just pure Newtonian fluid. Then we had baseline RO and air. So we injected some atmospheric air in there. And then we had baseline water, air, and nanobubbles. And when it comes down to the HVS piece, that was a good baseline to go from. So on the left hand, on all of these columns here, on the very left, you'll see pressure fluctuations. So we noticed that at the wall, if we measure the pressure, the standard deviation of the pressure per time, that's what we measured because we wanted to see the friction on the wall. So you can see for the first part, there's different flow rates. And then on the that's at I think 70% of the pump rating right there. And then in the middle, it was 85% of the total pump. And on the very end, it was 100% of the pump. And I believe it was around 70 gallons per minute at the maximum flow rate. So, but look at the far right, that's the HVS, the gray. Look how it had way less pressure fluctuations at the boundary layer at the wall. So that was really exciting finding for us in the lab. Then we tried different media. So HVS nanobubbles, I mixed a little bit of guar in there to give us some non-Newtonian properties, and you know why? So I could suspend the solids. And so we did guar first, and then we added some frac sand in there to see how that affected the flow regime with this vortex barbell valve. The reciprocation structure stability, this was an interesting test. So we stopped and started with respect to a pump cycle. And then what you're seeing here on the very top is you're seeing before the VBS, and then after the VBS. What I thought was really interesting, through that middle, we know from SPE papers that the Vmax, which is the maximum velocity on your pump stroke, is equal to 3.14 times VF. So there's pi again, it shows up in the formulas. But what's really interesting is when we looked at the pressure node on the bottom of the 90-degree acrylic pipe after the valve, you'll see on the graph, that's the dotted line, that pressure stayed stable for a little bit longer. So that means it didn't slump and we didn't get pressure fluctuations down before it stabilized itself. So that was a really good finding. Then we look at the trajectory of the vortex. The beautiful thing about this, we looked through thousands of videos and we found the same structure. So a bubble we traced from A, B, C. Those are the lasers in there for our guidance. On a 2D, it follows a beautiful sinusoidal waveform. If it's 3D, imagine it turning like this. So here's a nice visual of the sinusoidal waveform. It's almost kind of mesmerizing, but what I want to draw your attention to is the wall. You see how the gas molecules, this is slow motion, they look elongated. They're actually round, but it's just the velocity tracer. You can see the direction and they're not hitting the pipe wall. So that really helps us with respect to friction. Also, with the gas, you don't see it accumulate, and at the top of your stroke, you don't get that gas-liquid interface when your travel valve comes down. That's with a certain amount of gas, of course. If you have big slugs of gas, that's when we look at maybe an eccentric, gas separator. So this is the really exciting piece. When we started down this journey, we thought, yeah, it's hydrostatic that closes the valve, right? It's the fulcrum that works. Well, no, what we saw in the lab, it's actually hydrodynamic. So here's what hydrodynamic or hydraulic valves do. When you open the valve, so on the far left top side, you'll see water flowing through the valve. When I stop it, there's a little back pressure that occurs, and then that moves the valve just back enough so the conical shape and the high cross-section area where the high pressure part is on the graph, on the picture, and the low pressure part on the graph, and the seal causes a force from high pressure to low pressure. So we're getting a beautiful seal as long as we put high pressure across these valves. This is an example of the video. You see it moves just a little bit, and then the hydrodynamic force takes over and it closes. And this is at 90 degrees. So there's no hydrostatic on this. So this was a really awesome, exciting discovery in the lab. So now that we have thousands in the field, we make sure that we listen to our pump shop technicians. And one thing that we have to make sure that all of our pump technicians know, as well as the clients, is how to test these. Because the normal API test right now for the ball, it will change slightly for the barbell, but not too much. We have to make sure that barbell is within a 5-degree range, probably up to 10, but 5 degree each side. And if it's on there straight, then it'll test well in the lab. So all of them have come back and tested well if the right procedures are followed with respect to this new API procedure. The HVI solids and slugs enter the valve and get dispersed by the valve. So this is an interesting part, because when that big, it looks like 3/4 of the pipe is full of sand. And then as it goes through the valve, that sand comes up and distributes itself in the vortex all the way in the pump. So if you shine a laser past it, you'll see a pretty even flow profile and you won't even see the solids afterwards. So that helps us understand that this valve at that 70 degrees really does help us with the sand. So we keep it moving in a vortex through the pump in the tightest cross-sectional areas, and we know we're going to have a great solids pump moving forward. So here is a video of the frac sand. At the very end of our experimentation, we just dumped in a bunch of frac sand suspended by the guar. But as you can see, as this frac sand comes through the pump, that it is a big slug, and when it starts to go through and hits that valve up top, it starts to create a vortex afterwards. So we wanted to capture the slug from the end to the beginning, and as you see it coming through the valve here, soon enough we'll shine a laser at the end. You see how it comes through that valve, gets distributed through. There is more space in this valve than a regular valve as well, in the smaller cross-section area. But it takes that solid and distributes it and puts it all the way through that velocity profile. So that laser shining on there shows that the sand is suspended inside the shear planes inside above the valve. So that was a really exciting part of our experiment. It was just at the very end. So now we know when it comes to the slugging part of it, if it's enough sand to slug it with a lot of gas, that's when we've seen, okay, well, that's probably too much sand for this. But if you get a fair amount of sand, this valve can handle it. Then we go to the microfield data analysis. So this is interesting. A company came in and said, we'd love to do an SPE paper with you guys, and we'll share the data with you. And based on their 90 wells, they had, I think, at 32%, it says on here, an extra fluid produced when it came down. It was 127 days after installation. They were at that 60 degrees. So it was a nice marry between lab and field. I always like to control as much variables as possible. And the interesting thing about this is when they went deeper with the 14 wells out of the 90, you can see an increase, and it was a 143.5% increase. That goes back to our original comment that if you have more fluid head on your pump, you're going to help that pump get more fillage, and you're going to have better production when it comes down to your overall well going deeper into it. So here's the notes from the project. The installation and the companies and the laboratory results, the field data. We did multiple installations, and it revealed valuable information and considerations on the optimization of the HPS. The pump placement, this is another thing that we looked at. We got to watch our dogleg severities. So at 15 degrees, we kind of say that's almost the limit of where we want to go, and when the friction takes over and your failure frequency increases. However, some people are really putting a lot of guides on, and it's helping them kind of control, and the erosion of the tubing is getting better when it comes down to just having more wells under your belt. Surface equipment, have a rod rotator, have it consistent because you don't want it laying on that one side. Hardened valve rod guides, very important as well. You're going to have a lot of loading on your valve rod guides. Make sure those are stellate line, maybe double stellate line. We're just seeing certain parts that take more abuse than other ones. For shallower wells, sometimes we're using polypack plungers, but in general, we're looking at more grooved plungers and a sand twister up top, which helps move that solids above your plunger. So first we move the solids into vortex in our HPS, standing, traveling. Then we get it above inside the plunger where you have more room, and then above a sand twister, and then we're looking at guides in your suck rod string to keep that sand in the vortex and suspended. Also, strainer nipples down at the bottom. Let's make sure that there's lots of room in there and we don't create a lot of pressure drop. So these are just a few things that we've learned over the 3,000 wells that help us pump around the curve. So key considerations, deploying this around the curve. Let's clean out our wells. I know that's easier said than done. Also, rotation and slugs help. Some people come out, clean the well, and these fines are coming back. Those 1,000 micron fines love to lie on the bottom of the hole between 45 and 70 degrees. And I think they're under siltation, most of them, and they avalanche after a while. So you really kind of have to agitate them to some degree to get them out of the hole. Pump landing area, that's going to change with your well. If you're rotating and drilling, talk to your drilling guys and get it to a point where, hey, there's no dog legs here. This is going to be a good spot to land your pump. Sometimes it's 70 degrees, sometimes it's 90 degrees. We've seen all kinds, and it's really, your dog legs play a really important role. Stiff rods. So sinker rods with guides. So we're guiding them 8 times around the bend, and we're finding the stiffer they are, the The more guides they are, that's going to be better for your friction. We talked about moving the sand above your plunger. The sand twister moves it at that same angle. It happens to be pi. And it jets it into an area where it keeps it suspended in the annulus, right? Of course, your traveling valve, HVS valve, and traveler valve and your standing valve, we want those to be HVS. Down at that angle, you can try conventional valve, but you're going to get like 20% fillage. You get a lot of leakage. One more thing we're actually finding is that if you have a lot of gas in your well and you're down in the bend, that liquid falls back on itself. So we're almost creating our own reservoir with the eccentric gas separation unit. And so that might be an option as well. The POC, make sure we program our POCs. You're going to have friction. So POC, pump off controllers on surface, variable frequency drives, let's program those for the curve. And make sure we know our BHA and what stage we're at, what fluid levels we're at when we're programming our POC around the curve. Respace our pump. So the closer the travel valve gets to the standing valve, the more compression ratio we have, the more fillage you're going to get on your pump, the more efficiency you're going to get. So after pumping in the curve, I don't know how a week or a month, but you'll get to understand, hey, we've got to space this pump out. Different friction around the hole, different variables change. So your spacing requirements per time will change with your wells. Another interesting part is when you're coming around the curve, packers are somewhat difficult to get out of the hole, but some people do use them. In some cases, when we have an eccentric tubing with a lot of space around it, we're finding the fluid level gets down to your pump. So if you have an opportunity to change your tubing anchor to have a little more room for that fluid level to come down, we found that's also a valuable hint when it comes down to these pumping in the laterals. After this, what we've done is we've taken all 3,000 wells. We now have access to public production data, which is really exciting for us. So on a macro level as an engineer, I can go in and say, we've got 1,000 of these pumps in this field. Show me the ones with the new technology or old technology and give me the overall production. It's a few months old, but if you have a few years of data, you could look at before and after data. So these first ones are 2021 to 2024, and these are all companies. This is all public data, and you can see before and after. On the left-hand column is your BOE. We like to have gas and oil in our BOE. And on the right-hand side are the number of wells. So those are the diamond shapes. So for companies that are actually seeing declines in their reservoirs and their production, when they're putting these in, they're getting more fluid level to the pump, and they're actually seeing increases in production, which is really exciting. Here is another study. This is the United States. And inside here, yes, some companies are doing different things than others. There's a whole bunch of variables involved, and you'll see that the before and after on a few companies, look at the well count, look at the before and after. They're having a lot of success. Study some of the BHAs, the procedures, and find out how they're getting it. There's another company on here, before and after, not so good, right? What happened with them? Well, we visited it and we looked at it and said, okay, well, there's a lot of stretch in the rod, right? So we know that stiff rods really help, and maybe a really flexible rod around a bend doesn't give you the compression ratio, right? So that's another good lesson learned. So we like to learn from the ones that are successful and the ones that aren't. So I've got some key considerations for production engineers out there. When you come with your team and you learn from the service company about pumping in the curve, bring these points up to all of your engineers and go through them all and have an open discussion, right? About pre-pump well cleanouts, ensuring they're clear. What do we do? Talk to your fracking crew, completions crew afterwards. If you can get a clean out, great. If you got slotted liners, great, keeps the solids out. If you can't, take it on your own hands and say, we're going to try to clean as much of this well as we can. Optimal landing zones. Talk to your group about that. Solids management. What are we doing with solids? Are we studying them? Are we getting D50 size analysis? Do we know what kind of solids we're dealing with? So that's a good thing to bring up. Valve selection, of course, right now we have the one. We are developing different types, but for now this one is working really well in the field. POC adjustments. Regular POC adjustments are important. If you have a well, doesn't have a POC, you set it up, but just please respace it. Gas separation, depending on your amount of gas coming at you, talk about a plan. Is it a small amount of gas? Is it a large amount of gas? Tubing anchor design, like I did mention before, that's playing a big role. There's a lot of pinch points in your BHA, and the tubing anchor selection actually, in some cases, helps you increase your production by 30%, we've seen, by just changing the tubing anchor. Friction management, extremely important. Let's balance the amount of extra production and keep our failure frequency lower. And we can do that by following some of these. Solids analysis, these are something that's ongoing. So it's not just about getting understanding at the beginning, it's kind of tracking them all the way through. How does your company handle solids? And communication, obviously number one, right? Let's get our service guys, operations, guys in the field, production engineers, let's get everyone talking and make sure that we communicate the right plan moving forward, and as we're going, let's monitor things together. So overall, Q2 right now has about 50 service locations, 50 plus, and with recent purchase of Lufkin Downhole, we've expanded. We've got more manufacturing, more pump shops. So if you see an area in these oil fields that you're at, you can call your local sales gentleman. He'll have the product information. And if you need to get engineering involved in the deep level, I'm always here. My team's always here for you. Once again, my name is Corbin Coyes, and please reach out with any questions, comments. I love to talk about the science, love to talk about field results, and we're always evolving. We're trying new designs, and we really appreciate the operators that come out that want to try new technology, keep us in tune with what's going on in the field. Thanks so much.